two projects. We'll talk about two projects which have made up most of the work in my PhD, and both of them use asteroseismic ages in particular to make inferences on the chemical history of the galaxy. So the first one is about investigating the galactic metallicity gradient with asteroseismic ages and its evolution over the history of the disk. So when we look radially through the disk of the Milky Way, we can see that the stellar metallicity is not the same everywhere. It tends to be higher in the center of the disk and decreases as we move towards the edges of the disk. And this is a feature of the disk which is predicted by models of inside-out formation. So the better where the center of the disk forms first, and therefore you have more generations of stars which are born and die and enrich the medium from which the rest of the next generation forms, and produce higher metallicities than you have at the outer edge of the disk because it formed later. So the better the constraints we can place on this gradient, the better observations we have to compare to models of the history of the Milky Way. We have to be careful when we're talking about the radius that we know which one we mean. So we could be talking about the galactocentric radius, which is where we observe a star today. We could also be talking about the guiding radius, which is the radius of a circular orbit with the same angular momentum as the true stellar orbit. But we could also be talking about the birth radius, which might not be the same as either of those things. The reason for that is that stars can migrate to different orbital radii. And we can see that effect when we look at the metallicity radius plane as a kind of blurring of this relationship. So the stars spread out, because if we expect stars to be formed on this line in this plane, then at their birth radius, then if we see a star today which doesn't lie on the line that we expect, we can infer that the distance it's moved is because it's been shifted in its radius by radial migration processes. Those fall into two broad categories. So first we have blurring, which is an observational consequence of the eccentricity of the stars. So for stars on an eccentric orbit, at the particular time we observe it, we might see it closer to its apocenter or pericenter radius, so it will look further or closer to the center of the galaxy. We also have processes of churning. And in those cases, you have an angular momentum exchange with non-axisymmetric features in the disk of the Milky Way. So that's the bar or the spiral arms. And that means that the guiding radius is no longer a good approximation of the birth radius. Because your angular momentum has changed, your guiding radius has also changed. Whereas in the case of blurring, if we work in the guiding radius, we should be close to the birth radius because we don't see the effect of this eccentricity. So in the work that we do here, we choose to work in the guiding radius. So keep that in mind throughout. Once we have a sample of stars where we have chemical information for the metallicity and dynamical information for the guiding radius, if we can add in information about the age, then we can place good constraints on not only the metallicity gradient as it exists today in the disk, but also its evolution over the history of the Milky Way. And the tool that we use to do that in this work is asteroseismology. So here we just use the global asteroseismic parameters. So that's nu max, which is the maximum oscillation power, the frequency of maximum oscillation power of this Gaussian envelope, where each line here is a resonant frequency of oscillation in what we call a solar-like oscillator. And we also use nu max, delta nu, which is the large frequency separation. So the separation between oscillation modes of the same angular degree is pretty regular, and this spacing scales with the density of the star, and nu max scales with the surface gravity. So if we have constraints on both of those, we can get a good constraint on the mass. And here we're really interested in red giant stars because they're intrinsically luminous, so we can see them over large ranges. And their age is very tightly correlated with the total stellar mass because it's more or less determined by the main sequence lifetime. So as you can see here, we have a tight relationship between red giant age and total stellar mass. So with constraints from asteroseismology, we have a powerful tool to date stars, which is great for galactic archaeology. In this work, we have a sample of about 6,000 stars where we have robust spectroscopic parameters from APOGEE, astrometry from Gaia DR3, and also homogeneously determined ages from K2 asteroseismic observations. And from this sample, we down select stars in the thin disk in two stages. So we select a low alpha population because the high alpha stars, which are enriched in alpha elements, tend to be associated with the classical thick disk and the halo. So we get rid of those, and we also pick stars where their orbits are kinematically cool and that stay very flat within the disk. So we make a cut in the maximum excursion away from the disk during this total stellar orbit. And that leaves us with about 700 stars. The first thing we do with this data is fit it in bins of age. The model we assume is not a narrow straight line, but is actually a linear relationship convolved with a Gaussian. And what that means is that physically, we're not saying stars must be formed in the galaxy on a very narrow line, but they can be formed with some Gaussian spread around this relationship, which can come from differences in star formation history or gas mixing in the interstellar medium. So that gives us 3 fit parameters. So we have a gradient, an offset, and a spread around the line. And we constrain all these parameters by using MCMC to explore the parameter space. And we do that for many realizations of the ages. Because our age posteriors are not particularly narrow, this allows the stars to move between different bins of age as needed. So here we see the results of this analysis in 6 bins of age, where the points show where the star is binned according to its median age. So like I say, this particular star might in some realizations move into this bin, but all of that is factored in with the uncertainties. Our bins have to be wider at older ages because the age uncertainties are a roughly constant fraction of the total stellar age, something about 25% in this sample. And that means that we should use wider bins at older ages to account for these broader posteriors. So we see 2 pretty clear features in these results. The green line here is the line of that we get from our analysis. So we're using M and B, and the filled region is the intrinsic spread. So we can see that our gradient flattens as we move towards older ages, and also that this spread increases. And this is a bit easier to see in a slide with the summary here. What we have is the gradient, the offset, and the spread as a function of the stellar age, with a point for each bin based on the position of the median age of the population in the bin. The red error bars show the uncertainty that you get from a single realization of the data, so not taking into account the uncertainty on the ages, and the black error bars have everything folded in. So this is basically showing that we're not dominated by the uncertainty on our ages. They add about 30% to the total error budget. Overall, we see that the gradient flattens monotonically as a function of age. And we see particularly that we don't have very good resolution in the offset. Here we show the average metallicity at the solar radius, so at about 8 kiloparsecs, which looks to be slightly substellar metallicity over the whole history of the disk, but it's very difficult to say within our error bars. And finally, we show that the intrinsic spread increases as a function of age before a plateau in the oldest stars. This is the interesting feature if we want to talk about radial migration processes in particular. But it's difficult to constrain in bins because, of course, we don't have mono-age populations in the bin. We only have an approximation to that. So any spread in the population will be conflated with the underlying physical effects of this spread around the metallicity gradient. So since we have a larger sample at our disposal, we'd like to try to do a bit better than that. And to do that, we take a hierarchical approach. So we construct a hierarchical Bayesian model for our data set, where now instead of forcing the gradient, the offset, and the spread to be constant within a bin, we allow them to vary for each star according to some rule which applies to the whole population. The rule that we choose is that each parameter should vary linearly with age, and that's driven by 2 reasons. First, there isn't really a strong physical suggestion that we should do something different to that. The results in the bins don't have really enough resolution to say that we're not consistent with a linear relationship. But also the more parameters that we add here, the more difficult the space becomes to explore in our analysis. So keeping this number low is favorable in terms of getting to an answer in a reasonable timescale. We do have to make 2 small changes to this. So we would like to work linearly in age, but actually because the age error bars change along the age axis, as I said, it's a constant fraction of the total stellar age, the parameter space is too complex to explore. So instead we work in the log of the age. And we also take the spread to be an exponential, which is linear in the log of the age, because we don't want it to become negative. These are the results from our hierarchical analysis. So the points here show the same thing as before, the results from the bins, and the green line is the result of the HBM, which is curved, as I say, because we worked in log age, but here we plot in age, and the filled region is the uncertainties on each of the parameters. So the main thing to notice is that we have very good agreement with all our parameters at almost all ages. The gradient seems to be a little bit flatter in the bins than in the HBM, but fully consistent within the uncertainties. We have much better resolution for the average metallicity at the solar radius than we do in the bins. And that's a little bit difficult to explain why the HBM is doing so much better here, but it does definitely constrain us to a subsolar metallicity at this radius, which is one of the things that suggests that the sun was probably born closer to the galactic center and has since migrated outwards to its current location. And in the case of the spread, what we see is really quite good agreement between the HBM and the bins, which is encouraging because it means that what we see in the bins is not dominated by the fact that we are doing the binning. We're completely free from population size effects in the HBM. And the fact that the spread shows roughly the same scale is an encouraging feature. There does seem to be some oscillation around the HBM. So here we have a slightly increased spread, slightly decreased, slightly increased again. And these actually line up pretty well with the size of the population in the bin. So that might be a small perturbation on top of the total effect. The stars on the outside here are quite interesting. We would naively expect from models of radial migration that the older the star is, the older the population is, the more spread we should have, because older stars have had more time to move away from their birth radius. But we don't see that in our results. The HBM can't follow this curvature because we've made this linear assumption. But the fact that we believe all of these points leads us to think that we should believe this result from the bin as well. So what this suggests is that in this very old population, we really do have a reduced spread. And as I say, that's surprising when you consider radial migration. But actually, these stars are all older than 10 gigayears. And in most models of the formation of the Milky Way disk, it doesn't really start until about 10 gigayears ago. So although these have low alpha enrichment and are on very flat, very kinematically cool orbits, it's probable that they're not really thin disk members in the sense that we actually mean it. Today, and perhaps this reduced spread could come from the fact that at this point in the galaxy's history, the disk is very small and you have very centrally concentrated star formation. So you don't get a big mixture of metallicities, and therefore you reduce the spread that you see in this relationship overall. We can go on to compare our results to results from open clusters and also from theoretical models. So to take the clusters first, in orange, below about 6 gigayears, in the region where we overlap radially with these clusters, we show very good agreement. Beyond the region where our data extends, so beyond about 12 kilopar, beyond about 10 kiloparsecs, we don't see any. We can't see this region, so we don't see what these authors suggest, which is a flattening in the radial metallicity relationship in the open clusters. That's still a bit debated, but unfortunately, our sample isn't really deep enough to be able to give any insight on that question. In the oldest stars, we see a very clear metallicity offset between our results from field stars and the open clusters. And that's probably explainable by the survival bias for open clusters. So high metallicity open clusters, which are born close to the galactic disk, at the center of the disk, and then migrate outwards, are more likely to survive than low metallicity clusters, which are born in the outskirts of the galaxy and migrate in, because in the outer galaxy, the potentials which can disrupt the cluster are weaker. So for that reason, in samples of older open clusters, we tend to see more high metallicity results, and that probably explains this offset between the field star results and the cluster results. We also agree quite well with the results of the chemical evolution model. So the blue line is the chemical history of the Milky Way, which doesn't know anything about the dynamical processes in the disk. So the spread here is caused entirely by the bin size. And the blue points add in the effect of radial migration processes. So we see that there's a clear flattening in the gradient. It's especially obvious if you look in this oldest bin between the chemical evolution model and the full chemodynamical simulation. Again, up to about 4 gigayears, we appear to show very good agreement. But beyond that, there's a definite metallicity offset between the chemical evolution model and our results. And that suggests that maybe something in the underlying chemistry of the model is not quite consistent with what we really see in the Milky Way. So the outlook for this work, the first step maybe is to try and replace the linear assumption in the hierarchical model with the Gaussian process instead. So that would allow it the complete freedom to trace all the evolutionary features, to test our theories about the spread in the oldest stars. But that's very difficult to do because using the Gaussian process for your latent parameters is really slow. So yeah, it's not going to get done on timescales, which make it that feasible for my PhD, unfortunately. There's also lots more galactic archaeology to do with K2. So I remind you of how our sample looked at the beginning, and we've used really only 10% of it in this study because we're only looking at the thin disk. So there's lots of stuff to do with looking out of the disk as well. To take an extragalactic angle, we can also ask whether the migration that we see in the Milky Way could be present in other galaxies, especially Milky Way analogs, where we expect most things to be similar, but we actually observe quite a large spread in radial metallicity gradients. So the better we can constrain how much of the changing gradient and the spread around it can be caused by migratory processes in the Milky Way, the better we can understand how many of those galaxies are really Milky Way analogs and how many are not so similar to the Milky Way for reasons that we don't understand yet. Okay, so that's the end of the first part. And now we'll talk about a second project, which is about getting better stellar ages for galactic archaeology projects like the one I just described, by making better inferences about the helium abundance of individual stars. So we really like low mass stars in galactic archaeology because they can be long-lived and therefore they probe all epochs of galaxy formation. But in low mass stars, the helium spectral lines are really difficult to measure. And that's just because the temperatures are lower, basically. So normally when making a grid of models for these stars, we have to assume a helium-to-metal enrichment ratio. And what that means is that from the measured mass, from the metal mass fraction Z, which we can measure, and the primordial helium abundance, we assume some linear relationship in the enrichment, delta Y by delta Z. And from these parameters, we can estimate the helium abundance that should go into our models for a given star. But there are lots of open questions about this. There's a whole range of methods for obtaining this ratio, some of which use clusters, some use the main sequence of K-dwarfs, where you see a slight broadening with helium abundance. But across all of the literature, you see a lot of different answers. So usually, especially more recently, I would say the answer is roughly 2 plus or minus 1, but you can find literature which covers a whole order of magnitude from 0.5 to 5. If you want to dig into this a little bit, you can find a good list of different methods here. Beyond the question of what the enrichment ratio should be, we also have to ask whether a single, particularly linear enrichment law is valid across the whole history of the Milky Way at all. So this is one example from the literature, but the features that you see here are common to many. So there's an increased spread at low metallicities, below about solar metallicity. And also, if you fit a line through all of this data, you would recover a primordial helium abundance, which is significantly lower than what we know from Big Bang nucleosynthesis. And both these features are quite difficult to explain at the moment. How much does this actually matter? Well, if we're interested in high precision stellar ages for galactic archaeology, then it matters quite a lot, because here you can see the fractional change in age. If you change the helium abundance in these two bars, or the helium enrichment ratio, helium to metal enrichment ratio, by really quite conservative amounts, and you can easily change the age by tens of %. So in an era when asteroseismic ages are making uncertainties of a couple of tens of %, maybe, as I say, 20, 25 in the K2 sample, making them a realistic possibility, then this really matters quite a lot. In the case of a red clump star that we use in our study, this changes the age by 3 gigayears for a star that is roughly solar mass and solar metallicity. And we also see that in the red clump, we have this change in luminosity. And that's the feature that we're going to exploit in this work as a proxy for the helium abundance. The reason that this works is that for true red clump stars, which have gone through a helium flash, so we're not interested in the secondary clump, the core on the first ascent of the red giant branch is fully degenerate. That means that you have very efficient electron cooling, so you can delay the ignition of helium in the core until it reaches a critical mass. And that critical mass is more or less independent of the total stellar mass and the metallicity. It does have a dependence, but it's very weak. So that means that all of these stars have a very similar core mass, very similar central conditions, and therefore a very similar total luminosity. And that's what leads to the observational overdensity on the HR diagram. What it also means is that the small differences that remain in luminosity, once we know the stellar mass and the stellar metallicity, we can attribute to differences in the helium abundance. And that's where this relationship comes from. So we compile a sample of stars, this time from Kepler, which have global asteroseismic parameters. We use them to get the stellar parameters, particularly the mass for this work, but also to make a robust separation between true red clump stars and stars on the ascent of the RGB or the secondary red clump. And the other important thing for this work is the luminosities, which we get from Gaia DR3 parallaxes. We compare all these observations to a grid of models at several positions in mass and metallicity, but in this grid, we don't assume any enrichment ratio. So that means that at each grid point, so at each mass and each metallicity, we have several models for different helium abundances. And here you can see 4 examples. And we see again that the luminosity increases as we increase the helium abundance from 0.25 to 0.34. But we can also see that the shape of the track changes. So it's not just a simple shift in luminosity that we're dealing with here. We also have no information just from these lines about how long a star spends at any given luminosity. To do that, we would need a little bit more information, and that's important because for a given star, we're much more likely to observe it at some luminosities than others. So we assign a fractional age of 0 at the start of the red clump evolution and 1 at the end. And we draw uniform samples in this fractional age, and that means that we draw the most samples at the luminosities where the star is likely to spend the most time. And we find that it spends nearly 90% of its lifetime at this low luminosity, and then has a very fast excursion towards high luminosities as it evolves out of the red clump. We can look at that in these distributions where we take our samples in fractional age, and again, we see a strong peak at low luminosity and then a shallow tail towards higher luminosities where the evolution is more rapid. And again, we also see that the shape of the distribution changes with the helium abundance. So this is good, and we can compare this to our observations. So in black here, I've overplotted a distribution of median luminosities over a Monte Carlo on our population. So what this means is that we take a subsample of our full population, which lies close enough to the solar mass and the solar metallicity, and we take the median luminosity of that population, and then we shift everything within its uncertainties, or shift the luminosities within their uncertainties, and compute the median again. And that's the distribution that you see here. So it tells us that for stars of roughly solar mass and solar metallicity, we have a helium abundance of between 0.25 and 0.28. This is nice, but the real power comes when you extend it to bins in lower and higher metallicity. So now we see that all the distributions move in absolute luminosity, but the important thing is that the black observational distribution moves relative to the distributions from the models. So at lower metallicity, we have a lower helium abundance of closer to 0.25, which increases with the metallicity to about 0.28 by the time we're above solar metallicity. And that is the signature of the galactic enrichment of helium. And we also do this in different bins of mass as well. So how can we make best use of this observational feature? We don't just want to compare the position in this plane of big populations. We'd like to do this on a star-by-star basis. So to do that, we would like to take a non-parametric approach, because this evolution towards high luminosities, though it's very rapid, is important, and it's not information that we want to throw away. So once again, we take our samples in fractional age, and we assume a linear relationship between the helium abundance and the luminosity for a given fractional age. So we basically draw a lot of straight lines through these points, point at 0 fractional age, point at 0.1 fractional age, etc. And then we take our observational luminosity with its error bar, and we compare many realizations of our observation to these lines in the bin which is closest to the star. And that gives us a distribution of helium abundances for an individual star with resolution which is not too bad. Now, this looks good, and maybe we can just take the mean here and maybe a standard deviation as an uncertainty, and then we've solved all the problems, and that's great. But unfortunately, not all of our distributions look quite so Gaussian, and particularly this long tail here, this is the thing that tells us that for this star with a higher helium abundance, the excursion towards high luminosity of the lower metallicity, the lower helium abundance cases is really important, and this is what we particularly don't want to throw away. So if we take a very, very naive look at our results, where we do just take the average of these distributions, we seem to see a metallicity helium enrichment ratio of about 1.5, which is very consistent with the literature. But again, this is very naive, and we're not making best use of all the information that we have at our disposal. And this is sort of the point that I'm at with the work now. I was asking the question of how we can use all this data to best effect. But we do see a couple of encouraging signs. So there is an increased scatter at low metallicity, but we don't really seem to see the same trend towards very low primordial helium abundances as is present in other studies. We also have a lot of data points, and that gives us the opportunity to resolve any structure that might be present here and try to shed some light on the question of whether or not there really should be one linear relationship through all the history of the galaxy. I think in the last couple of minutes, I'll just say something about the Gaia luminosities. So the precision of the Gaia luminosities of, like 5-ish% is the thing that really makes this work possible, because we need to be able to resolve the difference between the luminosity positions of these histograms, which are at 5 or 10%. But that also means that we're very sensitive to small changes in luminosity, like those that come from the Gaia 0-point offset. So in black here, you see the same distributions in helium abundance that I showed before for the same 3 stars. And in this work, we've assumed the Lindegren 0-point correction. So that's the recommended correction to the 0-point offset. But if we don't apply a correction, or if we apply a constant correction from elsewhere in the literature, you can see that we have a very noticeable shift in the overall helium abundance. So whatever answer we eventually come out with for our work is likely to be an enrichment ratio up to the assumption of a 0-point offset for Gaia. So the outlook for this work is to say that Gaia luminosities really make helium inference for individual red clump stars possible. But what we're trying to do now is really validate a statistical technique that will allow us to constrain the relationship better than has been done previously. And then hopefully next year, I will take this method and apply it to the data that I described in the first part of the talk and make a map of the helium abundance around the galaxy. And now I'm going to stop talking. Thank you very much.
Thank you, Emma, for the very nice talk. Let's see if we have a question from the public. In the meanwhile, I have one concerning the first part of your talk, when you showed all the gradients of iron with radius, with the not the galactocentric, the other one, the orbital. I don't remember how do you define that. So would it be possible to also investigate gradients of other elements and see if there is an agreement with the models?
Yeah, it is possible. We have all the tools now to do that. But in the paper that I'm finishing up now, we're only going to talk about the metallicity gradient. So it's next on the list. Yeah, all the information is there.
Okay. That would be very interesting. Let's see if anybody has a question. I don't see hands up. Another curiosity concerning the second part of your talk. Okay, there will be a question from Angela. When you showed the helium content as a function of metallicity, okay. Yeah, I see that over there. So does it, when you compare it with the other literature value, does it stand up compared to, because as far as I understood, typically the other measurements tend to imply a very low primordial helium abundance, while from your plot it looks like you're not that low. I mean, as soon as you approach the very low metallicity. Is that correct, or is just?
Yeah, so above about solar metallicity, then yeah, our points overlaid with points from literature studies would look pretty similar. We don't seem to see the same break that I showed in the plot from Luca Casagrande's paper. And at the moment, I think that's probably good news. Nobody has really been able to explain why in these kind of works you do recover very low primordial helium abundances, but for whatever reason, it doesn't seem to be present in our sample. And as I dig into that a bit more, then hopefully we can explain what the reason is. But it's definitely been an open problem that yeah, when you do this, you recover a primordial helium abundance, which is completely inconsistent with Big Bang nucleosynthesis, and it doesn't look like we're going to do that. So,
okay, I think it's very promising, very nice. Okay, we have a question from Angela.
Yeah, thank you. Very interesting. It's a curiosity. When you compared with the open clusters, you used the APOGEE results, the Occam sample. Yeah. Have you tried other samples? For instance, there is a sample defined by Gaia DR3. There are hundreds of clusters more. Maybe the precision is a little less than for APOGEE, but the number is 6 times more.
Yeah. So I've had
and
a look
at
of
course other sources.
Yeah. So I've had a look at the in the Gaia chemical cartography paper from earlier this year. They do constrain the radial metallicity gradient in their group of clusters out to, I think, 12 kiloparsecs. So they deliberately don't probe the region where we might have this break in the relationship. And the gradients that they come out with are reasonably consistent with what we find up to in the older population, where you continue to see a steepening in the gradient due to the survival bias for the clusters. But one of the concerns when we're doing this is that there can be, as I'm sure you know, the abundance offsets between the different surveys. So on this plot, we only show clusters where we know we're using the same metallicity, so all from APOGEE DR17, but it doesn't hold up too badly compared to cluster surveys from other sources. So.
Thank you.
More questions? I don't see any additional question. So let's thank Emma again for the very interesting talk, and see you next Tuesday for our astrophysics seminar. Thank you. Bye.